Okay, so let's look at the first exam for the fall 2018 uh, General Chemistry 1. Yeah, there is a slight typo here, right? That should be fall 2018. So don't get tripped up by that. But anyway, let's look at the exam 1 and let's start to work through it. Now it'd be useful for you to have a periodic table with you while you're going through this. I tried to record this by having a periodic table here, but it would be kind of awkward to kind of tab in between everything. But we will be looking at the periodic table, so have one available so you can follow along. So question 1, how many protons, neutrons, and electrons are present in the following species, right, in the following? So chromium 54. So first thing to realize, let me zoom in here, right, when we're dealing with notation for isotopes, right, we need to know what the numbers mean, right, and where the information is coming from. So let's start with the second one real quick, right? Let's look at this guy right here. So a couple of important bits of information. So let's start with the obvious, the Se. All right, so this is selenium, and remember, selenium is defined by the number of protons there are in the nucleus. Right, so we need to look at the periodic table, and if we find selenium on the periodic table, it is number 34. It is right below sulfur, and that number 34 is telling us, right, how many protons there are. Right, so the selenium tells us how many protons there are. Let me change colors here real quick. We notice that this is selenium with a 2 minus charge. Selenium with a 2 minus charge. So if I scroll over, selenium with a 2 minus charge, that means I've got to have 36 electrons over here. Remember, when we add electrons, we end up making a negative charge, right? We kind of have that reverse from what our typical idea is, right? We add electrons and we get a negative charge. All right, so let me erase this. Let me zoom back in here. So we've dealt with the protons, we've dealt with the electrons. Let's deal with the neutrons. Now, let's pick a new color. Purple sounds good. That number right there, the 80, that is telling us the total number of protons plus neutrons in this particular isotope. So our answer for our neutrons would be 80 minus 34, right? 80 minus 34, so we end up having 46. So these numbers that I'm circling in purple, right, they are telling us the total number, right, of protons plus neutrons. All right, so that being said, if you want to pause the video right now to fill in the rest of the blanks, I'm going to go through and I'm going to work through the rest of them here and fill in the answers. I'm not really going to explain where I got the other ones from. Hopefully, right, we've got it that protons comes from the definition of which element we're looking at. Electrons, right, we take a look at the charge. If it's neutral, they have to be equal. And the neutrons comes from our isotope, or which isotope we're looking at. So I'm going to fill in the rest of what we had. 28 down here, 32 for germanium, and we have 40 neutrons there. All right. So there we go. Protons, neutrons, and electrons. Okay, question 2. We're looking at isotopic abundance, right? So gallium has two naturally occurring isotopes, gallium-69, and then it gives us some info, and gallium-71. It asks, what is the mass of gallium-71? So remember, we need our equation, right? And so we're gonna need our periodic table and look up the atomic mass for gallium. And if we look it up, it is 69.723. That's the periodic table that I'm using. And remember, the value on the periodic table, the 69.723, this comes from the sum of the percent abundance. I'm just going to abbreviate percent abund, right? The percent abundance times the weight. Well, I should say mass, just to be technically correct, right? Times the mass of that isotope. So let's say for just a second that gallium had 15 isotopes. What we need to do is set up an equation where the percentage of each one of those 15 isotopes, right, the percent abundance of each one of those 15 isotopes times its mass, right, would be equal to the 69.723. Right, so if we had 15 isotopes, we'd have to do this equation, or we have to set up a pretty long equation. But we don't, we've only got two. So now we just got to fill in the blanks, right? So 69.723 is equal to, let's look at our first isotope here. I'll do it in red, right? Let's take a look at gallium 69 here. So the percent abundance is 60.11. Now remember, to make our math a little bit easier, we're dealing with this in decimals, so 6011, right? That's our percent abundance times the mass, 68.9256 AMU, right? Plus, right? We're dealing with the sum of, and let's grab our purple, right? We need our second isotope, so gallium 71. Now the percent abundance of gallium 71, right, is equal to 1 minus 0.6011. We've only got two isotopes. They have to add up to be equal to 100%. So we can just do 1 minus the abundance of gallium 69. Okay, so I'm just going to erase that and give us our answer in there, 0.3989. And here is what we don't know. We don't know the mass of isotope 71, right? That's what it's asking for. So there's our X. So if you want to pause here and see if you can solve this equation, I'm going to go through and I'm not going to show everything exhaustively, but hopefully we can get down to it. 69.723, right? This is equal to 41.43 plus 0.39, whoops, I missed my 3, 0.3989 x, 28.293 equals 0.3989x, x equals 70.9276. Awesome. So hopefully you were able to follow along with that. Two key parts: understanding your abundance, right? Everything has to add up to be 100%, and then knowing what formula to use. All right, let's look at number 3. So number 3 is more of a conceptual question. It says, suppose you have a volatile liquid and that it's in a sealed jar. So what happens to the mass of that sealed system if the liquid is vaporized? So we have a jar, it's filled with some liquid. We turn that liquid, right, into a gas, and it's asked what happens to the mass of that sealed system. So remember, basically this question was asking, do you understand the law of conservation of mass? Right? Matter or mass or energy cannot be created nor destroyed. Right? So if we have a sealed system and we just turn a liquid into a gas, we're not changing the mass for anything that's in there. Right? So our mass is going to be constant because we're making a couple of assumptions here, right? We've got some jar, right, that's sealed, right? Later on in the semester, we'll talk a little bit more about, the system and the surroundings and what might be going on in this particular jar. But for the moment, we're just asking what happens, to mass in a sealed system and what happens if it evaporates. Basically, another way of thinking about this is, let's say we have a jar and we've got 100 grams of liquid water in there. If we turn that 100 grams of liquid water into steam, right, we would still have 100 grams of steam present, right? Water in its gaseous state. So that mass is going to remain constant. Now, if we would talk about energy, right, that might be a different question here, right? We'd have to turn that into steam somehow. So we'll talk about that in a later chapter. All right, suppose a container has 1.45 liters of gas. We've given a density, and we're asked what is the mass of the gas in kilograms. So a couple of things to note, right? Here we have units of liters. Here we have units of milliliters. Okay. Here we have units of grams. Here we have kilograms. So we're going to have to do a couple of conversions along the way. So let's plot out our roadmap. We've got to convert liters into milliliters, right? We've got to convert that into grams and then into kilograms. We're given liters of gas. We're going to convert that into milliliters of gas, right? And then we're going to convert milliliters of gas into grams. And we do that using the density, right? So converting volume to mass, right, we need density. And then we're going to convert grams into kilograms. So let's get this started. 1.45 liters of gas. Convert that into milliliters. That's what we said we're going to do first. For every 1 liter, we have 1,000 milliliters. Now we're in milliliters. Let's convert that into grams. For every 1 milliliter, you know what? Let me do this in a different color. Let me just clean this up a little bit. All right, let's do this in purple here, right? Converting for every 1 milliliter, we have 0.71 grams, right? That's using the density here. Let's just color that in purple over here, right? And we'll finish up in, oh, it seems like a green day. Let's do green. We'll finish up in green over here. We're converting grams. For every 1,000 grams, we have 1 kilogram. And I got my answer to be about 1.0295. Now, if we want to worry about significant figures, you can, right? But for the moment, let's just focus on the calculations and how we get stuff set up. So liters to milliliters, right? Let's follow our units. Liters cancels out, milliliters cancels out, grams cancel it out, and we're left in kilograms. Wonderful. Number 5, calculate the mass of 2.25 times 10 to the 22 barium atoms. So mass is in grams. So we have to go somehow from atoms, right, our unit of atoms, into grams. Now we're going to have to take a slight detour. We're going to have to go from atoms to moles, moles to grams. Or let me clarify here. The way I'm going to go is from atoms to moles, moles to grams. There is another way to do it, right? But I think this is the one that's, I won't say easiest, but the one that maybe makes more logical sense to me at least. So atoms to moles. Let's get this set up, right? So 2.25 times 10 to the 22 atoms of barium. Now, how do I convert atoms into moles? Well, here's where we need to know what Avogadro's number is, right? So 6.022 times 10 to the 23rd atoms of barium, right? Oops, get a lowercase here, right? Atoms of barium for every 1 mole of barium. This value right here, right? Let's put that in green. This value in green, right? That defines what a mole is, right? A mole is 6.022 times 10 to the 23rd of anything. In this case, we're saying that we need that many atoms, 6.022 times 10 to the 23rd, for every 1 mole. Okay? Let me clean this up to give myself some space. Right? So we're going atoms to moles and into grams. Now we take a look at the periodic table. Right? We get the atomic weight, the atomic mass of barium, right, in red here, right? So for every 1 mole of barium, we're going to have a mass of 137.328 grams. And my answer is 5.131 grams of barium. So in red, right, I just pull that information from the periodic table. All right, now number 6. This was probably the trickiest one on the exam. But basically number 6 is kind of almost the opposite direction of number 5. Because let's take a look at what information we're given. I am saying that I have 20 grams, and I counted that I have that many atoms in that sample, in that 20 gram sample. Now let's pause for just a second. Let's do a little mind exercise here. Let's say that instead I had said that I have a, let's say instead I had a 32 gram sample of some unknown element, and I counted that I had 6.022 times 10 to the 23rd atoms in that sample, right? So let's say, right, we'll do a slightly different question. I had a 32 gram sample and I had 6.022 times 10 to the 23rd atoms. What would be the identity of this element? Well, here's where we have to think, right? The number of atoms doesn't really tell us much directly. But if we convert this into moles, right? If we convert this into moles, that's 1 mole, right? 6.022 defines 1 mole. And if I have 32 grams in that 1 mole, right? That's what sulfur is equal to, right? So if you take a look at the periodic table, it's telling me that for every 1 mole of sulfur, I have 32 grams. So we're going to have to take the same approach here for this problem, right? We're going to have to convert atoms into moles and then divide our grams by the number of moles that we have to get units of grams per mole. Okay, so let me clean this up. And let's start that conversion, right? So atoms are going to get converted into moles. So let's do that. 4.95 times 10 to the 23rd atoms of our unknown divided by 6.022 times 10 to the 23rd atoms for every 1 mole. Okay, and this was equal to 0.822 moles. Which means now, right, this number here, right, the 0.8222, I have that many moles in a 20 gram sample. So for every 20 grams, I have 0.822 moles. And then if I divide those two, my answer comes out to be about 24.33 grams per mole, which is magnesium. All right, so that's the end of page 1. We're going to pause the video here, and the next video will be covering page 2. So I'm going to zoom out so we can just see everything here if you guys want to pause and look at the answer key, so to speak. And we will move on to the next page in the next video.